This is Drone Nation, the show about flying drones for fun, business, and a real career. Your hosts are Robbie and Terry, both 15. Every week they break it down so you actually get it.
Drones for fun, business, and a real career. I'm Terry.
And I'm Robbie. And today we're cracking open the machine itself, how drones are actually engineered and built.
Like, what makes a drone and not just a fancy frisbee with delusions of grandeur?
Exactly. So at the core, every drone has four main systems: a frame, motors, a flight controller, and a power source.
The frame is basically the skeleton. It holds everything together and takes a beating every time you land creatively.
Most frames are made from carbon fiber because it's incredibly strong and super lightweight, about 5 times stronger than steel by weight.
5 times, that's wild. And weight matters so much because every extra gram costs you battery life and flight time.
The motors are where physics gets exciting. Most consumer drones use brushless motors, which have no physical contact between spinning parts.
No contact means less friction, less heat, less wear. They last way longer than the old brushed motors.
A typical racing drone motor spins at around 25,000 revolutions per minute. That's not a typo.
25,000. My brain does about 4 revolutions per minute on a Monday morning.
Ha! Now the propellers convert all that spinning into actual lift, using the same aerodynamic principle as airplane wings.
The blade angle, called pitch, determines whether you're optimizing for speed or for lifting heavy payloads.
High-pitch props move more air per spin, great for racing. Low-pitch props are efficient, great for carrying cameras.
And here's where it gets brainy. The flight controller is basically the drone's nervous system and brain combined.
It's a tiny computer running software that reads sensors dozens of times per second and adjusts each motor individually.
Without that, the drone would just flip and crash instantly. Hovering looks effortless, but it's constant microsecond corrections.
The key sensor is the IMU, Inertial Measurement Unit, which tracks tilt, rotation, and acceleration all at once.
It's the same technology in your phone that knows when you rotate the screen, just way, way faster.
Flight controllers can process sensor data over 1,000 times per second. That's the difference between hovering and tumbling.
1,000 times per second. My homework takes 1,000 seconds per problem. Very different energy.
Power comes from lithium polymer batteries, LiPo, which pack enormous energy into a surprisingly small and light package.
The trade-off is they're kind of temperamental. Overcharge them, puncture them, or short them, and things get spicy fast.
Spicy meaning actual fire, so engineers design battery management systems to monitor voltage, temperature, and charge cycles constantly.
Engineers also have to think about ESCs, electronic speed controllers, one for each motor, translating commands into precise power delivery.
The flight controller says spin faster, and the S key makes it happen dozens of times every single second.
And all these parts have to talk to each other with zero lag, which is why the wiring and protocols really matter.
Most modern drones use a communication protocol called CAN bus, originally designed for cars, now everywhere in aerospace too.
Technology traveling from road to sky, that's honestly such a cool crossover episode for engineering.
Then there's GPS, magnetometers, barometers. A drone knows where it is, which way it's pointing, and how high it's flying.
Remove any one of those, and suddenly your drone doesn't know up from down. Literally.
That's why engineers do something called sensor fusion, blending data from multiple sensors so one bad reading doesn't crash everything.
It's like asking 3 friends for directions and averaging the answer. Smart, if your friends are gyroscopes.
When you design a drone, you also have to think about fail-safes. What does it do if it loses signal?
Most are programmed to hover, return home, or land safely rather than just drop out of the sky.
Engineers call that graceful degradation. The system fails in the least catastrophic way possible. Very reassuring concept.
Very reassuring. I want graceful degradation in my life, honestly. Just gently hover when things go wrong.
The whole field keeps evolving fast. Better batteries, smarter controllers, lighter materials, all pushing drones to do more with less.
And if this sounds like your kind of puzzle, motors, code, physics, problem solving, drone engineering is a real career path.
Aerospace engineering, electrical engineering, embedded software, all of these feed directly into building the machines we love to fly.
So next time you see a drone humming overhead, remember there are about 1,000 tiny engineering decisions keeping it up there.
Every hover is a small miracle of physics and code. Pretty cool that humans figured that out. See you next week on Drone Nation.